Chemistry of Textile Fibers and Polymers. My YouTube channel is AKRC Learn Textile Chemistry. The purpose of opening this YouTube channel is to share my knowledge with student researchers and people working in the textile and related fields throughout the globe. I am Professor Dr. Ashim Kumar Rai Chaudhary, ex-professor and HOD, Government College of Engineering and Textile Technology, Srirampur, West Bengal, India. Introduction. Clothing and textile are important in human history. Clothing may have been used 0.1 to 0.5 million years ago. Worldwide textile production in the year 1975 was approximately 24 million metric tons, and in the year 2020 it increased to more than 113.8 million metric tons, of which natural fiber production was 25.2 MMT and man-made fiber production was 87.6 MMT. In the year 1990, the production of synthetic fiber first crossed the production of cotton, and next 20 years it became double. In the year 2020, synthetic fiber production accounted for 64%, of which polyester production was 54% of the global fiber production. Projected production by 2030 is 149 MMT. Approximately 17.5 kg per person will be in use in the year 2030. This is as per www.statista.com, October 30, 2023. Characteristics of textile fibers. It should have high flexibility, high fineness, a high ratio of length to thickness. It should have sufficient strength to resist breakage during manufacture and use. It should have enough thermal and chemical stability. Extensibility of 5 to 50% depending on the end use. Many natural fibers are not sufficiently long, flexible or strong to be used as textile fiber. The properties of vegetable fibers depend on soil, feed and other climatic and environmental conditions. The properties of animal fibers are largely non-uniform and depend on breed's geographical location. Man-made fibers are largely uniform and greater controls can be exercised over their production. However, little variations in the production of man-made fibers can give rise to significant variations in durability, strength and some other properties. Physical structures of textile fibers. Each individual fiber is made of millions of individual long molecular chains of discrete chemical structure. The morphology, that is the arrangement and orientation of these molecules within the individual fiber, as well as the gross cross section and shape of the fiber, influence the fiber properties. However, the basic physical and chemical properties largely depend on the chemical structure of the long molecular chains constituting the fiber. Degree of polymerization, or DP. DP is the number of units that repeats in a molecular chain. DP of cotton is about 10,000 and of viscose rayon about 300 to 500. DP of man-made fiber is determined by various factors during production of these fibers. Polymers. Polymers are made of monomers. Mono means one, mer means unit. Monomers repeat a large number of times to form a long chain or a molecule called polymer. Poly means many. Copolymers are formed from two or more different monomers. In copolymers, there is no definite regularity in the order of monomers. Some polymers may contain additional monomers which do not form part of the polymer chain and are incorporated to improve certain properties of the fiber such as affinity to dyes. Those are grafted onto the polymer chain as side grooves or branch. The figure shows the chemical structures of homopolymers, copolymer, grafted polymers symbolically. The rectangle, circle and triangle represent the chemical structures of three different monomers used in this figure. First one is symbolic structure of homopolymer, where each polymer chain is made of a single monomer. Three polymer chains are shown. Then for copolymers, each chain is composed of two or more monomers. Two such copolymer structure are shown. And grafted polymers, there are some monomers which lies as branch chain of the main polymer chain. Crystalline and amorphous regions. In crystalline solids, atoms or molecules are arranged in a repeating, well-defined pattern called a crystal lattice. Crystals have sharp, well-defined faces and exhibit symmetry due to their regular arrangement. They have distinct melting points. These regular arrangement extend throughout the entire solid. Long chain molecules are mostly oriented in a particular direction. In other words, the degree of orientation is quite high. In amorphous solids, there is no long range order in the arrangement of atoms and molecules. They lack a specific crystal lattice and exhibits a random, disordered structure. Summary: crystalline solids have an ordered repeating structure, while amorphous solids lack long range order and exhibits randomness. Both types play essential roles in deciding the physical and chemical properties of the materials. Polymers are generally made of both crystalline and amorphous region in two different extremes. Degree of orientation and degree of crystallinity. Orientation refers to the arrangement of polymer chains or segments in a specific direction. Degree of crystallinity is a measure of the amount of crystalline part in a polymeric sample. These are two important quantities that strongly influence physical properties of fiber. In amorphous regions, the molecular chains are not as well ordered, tending to a random coil configuration as shown in the figure. Essential properties of fibers. The fiber should have high molecular weight for adequate strength. Minimum molecular length should be 100 nanometer, that is 10 to the minus 9 meter. Linear polymers can form sufficient crystalline regions, permitting formation of adequate number of inter-polymer chain forces of attraction. Bulky and or branch molecular chain cannot come close enough to form a crystalline region. The presence of a sufficient number of intermolecular bonds is a must. Orientation. The extent and proportion of the crystalline and amorphous region may vary. In natural fiber, the variation is created inherently by nature, and in case of man-made fiber, the variation can be controlled during production. In some polymers, the crystalline regions are formed during extrusion and the subsequent drying process. Highly crystalline fibers have harsh handle and poor abrasion resistance. They are quickly damaged during rubbing. Then melting point. Synthetic fiber have specific range of melting points depending on the chemical structure, molecular weight and the degree of crystallinity. Natural fibers do not melt as they have strong interchain bonding and long chain. However, they may turn yellow and are damaged above specific temperature depending on the chemical structure of the fiber. 4 types of intermolecular bonds act in a polymer or textile fiber. First, hydrogen bond. This acts between hydrogen ion and negatively charged oxygen, nitrogen or chlorine atom in an adjacent polymer molecules. Natural fibers are inherently rich in hydrogen bonds. Second, van der Waals forces. These occur between closely packed polymer molecules. Both bonds are weak, but the presence in large number of hydrogen bond and van der Waals forces significantly contributes to polymer strength. Third, ionic bond. These occur between oppositely charged polar groups. These groups are stronger than above bond. Ionic bonds occur principally in protein fibers like wool and silk and polyamide fibers like nylon. Strongest and chemically most stable bond is covalent bond or cross-links. These are formed when two atoms share a pair of electrons. A low degree of cross-links, as in case of wool disulfide bond or elastomeric fiber, imparts a good to excellent elasticity. Classification of textile fibers. The type of textile fibers available globally are exceedingly large in number, and apparently it is very difficult to categorize under a few classes. Broad classification: natural and man-made fibers. Sources of natural fibers are vegetable, like for example cellulose, animal, that is protein fiber, and mineral, asbestos fiber. Other than there are refractory or ceramic and industrial fibers are also available, like carbon, glass fiber, metal fiber, etc. Vegetable fiber classification according to source of origin. For example, cotton is a seed fiber, flax, jute, etc. are bast fiber, seashell is leaf fiber. Animal fiber, there are broadly 3 types: silk, wool and specialty hair fibers. New sustainable natural protein fibers are casein or milk fiber and soybean vegetable protein fiber (SPF). Man-made fibers. Man-made fiber are broadly 2 types: regenerated and synthetic fiber. Regenerated example: viscose, polynoxing and lyocell. Synthetic man-made fiber: polyamide, polyester, polyacrylic fibers, polyalkyl and polyurethane. Detailed classification of textile fibers. Textile fiber can be broadly classified as natural and man-made fiber. Natural fiber are from 3 sources: vegetable, those are mostly cellulosic in nature; animal or protein fiber; and mineral or inorganic fibers. Vegetable fiber may be from seed like cotton and kapok; skin or bast, jute, flax, hemp, rami; leaf fiber, seashell, pineapple, abaca, etc. Fruit fiber, coir. Now, animal or protein fiber, natural animal or protein fiber are silk, wool and minor hair fibers. Mineral or inorganic fibers are asbestos. Now, man-made fiber may be natural polymers or refractory and related fibers. Now, natural polymers may be regenerated cellulose like rayon, viscose rayon, cuproamide rayon or lyocell, cellulose ester like acetate, and regenerated protein like casein. There may be other miscellaneous fiber like alginate and natural fibers. Now, synthetic fibers may be polyester, polyamide, polyvinyl, polymerized hydrocarbon like polyethylene or polypropylene, and synthetic rubbers. Now polyvinyl again can be classified as substrate with chlorine, substrate with fluorine, that is Teflon, substrate with cyano, and substrate with hydroxyl like polyvinyl alcohol. Classification of textile fibers as per chemical constitution: cellulosic, cotton, bast fiber like flax and jute, hemp, remi, leaf fiber like sisal and rayons. The number shows the figure numbers. Modified cellulosic, acetate, that is cellulose ester, protein fiber, natural, wool, silk, hair fiber and casein. Polyamide fiber, nylon and aramid, that is aromatic nylon. Polyester, terylene, dacron, CD, that is cationic diol polyester. Polyacrylic, acrylic fibers, modacrylics. Polyolefins, polyethylene and polypropylene. Vinyl, that is saran and Teflon, polytetrafluoroethylene, and polyurethane, spandex. Cotton fiber, that is cellulosic fiber. The most important cotton fiber is obtained from the seeds of cotton plant, and it accounts for about 50% of the global fiber production. The largest producers of cotton are India, China, USA, Brazil, Pakistan, Uzbekistan and Turkey. China produces 6,684 million tons, while India produces only 5.9 million tons per year. Starch and cellulose have similar structure, but starch uses 1,4 and 1,6 alpha linkages and has a branch structure, whereas cellulose uses 1,4 beta linkage and has a rigid elongated structure. The cellulose structure is shown in the above in the figure, and starch is below. The figure clearly shows that there is little scope of formation of hydrogen bond in case of starch, while lot of hydrogen bond can produce in cellulose, resulting it's a very strong, not solid, water soluble polymer. Cotton is very nearly pure cellulose. It consists of long chain molecules having 10,000 to 16,000 beta anhydroglucose units. Cellulose, the monomer of cellulose, is a disaccharide present in cellulose. 2 beta D glucose molecules joined together in the 1:4 portion as shown in the figure. Each alternate unit must be turned through an angle of 180 degree so that there is a high chance of hydrogen bond formation. Hydrogen atoms of all the hydroxyl groups are hydrogen bonded. These hydrogen bonds hold several adjacent cellulose chains in close alignment to form crystalline areas called microfibrils. Cotton contains about 70% crystalline region and about 30% disordered amorphous regions. Dyes and chemicals penetrate easily in the amorphous region, while crystalline regions are difficult to penetrate. Cellulose polymer is quite reactive because of these 3 free hydroxyl groups. Morphological structure of cotton. Each cotton hair is a single elongated cell having one tapered end and another open end cut from cotton seed. Ribbon-like structure of somewhat irregular diameter. It has periodic twists or convolutions about 150 to 300 twists per inch along the length of the fiber. It has kidney-shaped cross-section or similar to a collar stem. Central hollow channel of cotton is known as lumen. Innermost matured secondary wall is layers of well aligned at 23 degree and closely packed cellulosic chain. Fibular deposition, helical form with frequent unique reversal of the helix along the length of the fiber. Next, outer layer is primary wall. It is less crystalline, crossed to a tougher surface structure. Outermost layer is known as cuticle. It contains pectin, fat and waxes, etc., preventing entry of water, carrying dyes, etc. Important characteristics of cotton. It has high crystallinity, about 70%, and moderately strong. It is moderately strong fiber. It is about 20% stronger when in wet condition. It is densest fiber, having specific gravity of 1.54. Moderate heat conductivity, unchanged when heated at 120 degree for a moderate period. It is not soluble in common solvent. It is soluble in aqueous cuprammonium hydroxide and cupriethylene diamine. It is not affected by cold dilute acids. It has excellent resistance to alkalis. It swells in 20% caustic soda solution for a minute or so. Mercerization with improved luster, durability and moisture uptake of cotton material. Oxidizing agents such as hydrogen peroxide, sodium hypochlorite, sodium chloride are harmless in dilute condition but may damage cotton in higher concentration, forming oxycellulose. Bast fiber. Bast fiber, also known as skin fiber, is plant fiber collected from in between outer bark and central woody portion of specific plants. Most important bast fibers are flax, jute, hemp and rami. For all bast fiber, first the fiber is to be separated from the outer tissues by a process called retting. Retting may be by water, it may be dew or by chemicals. Multicellular, these bast fibers are multicellular, that is a number of fibers, units or cells are held together by natural adhesive. The fibers are extremely long and bamboo-like longitudinal cross markings. Bast fibers are classified as soft fiber and are flexible, while leaf fibers are classed as hard fibers and are stiff. Flax. Flax or linen is best and oldest bast fiber. It is mentioned in the Bible and also used by Egyptians, Greeks and Romans. In 2020, global production of flax was 3.4 million tons. Biggest producers of flax are Kazakhstan, about 31%, followed by China, Canada, Russia, United States of America and India. Flax is mainly cultivated for linseed drying oil used in paints and varnishes. Flax is very compact and difficult to dye. The chemical properties are similar to those of cotton. Good resistance to acid, base and chemical bleaches. Flax has resistance to insects and microorganisms except under severe moist warm conditions. Figure shows flax upholstery fabric as well as flax garment owned by a lady. Jute. Jute is native to India, Pakistan and Bangladesh. It requires water rating for 12 to 25 days. It is not very strong or durable as flax or hemp. Individual fibers are very short, about 0.1 inch, that is 0.25 centimeter long, and a number of short fibers are bundled together by an adhesive called lignin. These jute fibers are stiff and moisture retain is low. Shredding or falling of broken jute fiber is very common during handling. Jute has silk-like luster but changes to brown due to presence of 13% yellow color lignin. Jute is low cost, moderate strength and easy available. That's why it is popular for sacks, bags and packing material. The figure shows the longitudinal structure of jute, then cross-sectional view of jute fiber, and finally the jute fabrics, different types of jute fabrics. Hemp and remi. Hemp grows in 40 countries. Total production was 275,000 tons in 2019. 50% of this production produced in 4 countries: China, France, Canada and United States. Hemp is coarser than flax, darker in color and is difficult to bleach. It is strong and durable fiber. Length may reach 6 feet or longer. The fiber is very stiff and contains considerable amount of lignin. It is mainly used for coarser fabric, including sack material, canvas, ropes and twins. Remi or China grass production in 2021 was 10,134 tons. China produced 85%, followed by Brazil, Philippines, India, South Korea and Thailand. Rating is quite difficult and the fibers are separated manually or mechanized pulling, followed by degumming with plain or lime water. Fiber is white with excellent strength and luster. Strongest and most durable among the vegetable fiber is remi. The fiber is stiff and fairly coarse. The cells of the fiber are very long and the cross section is irregular in shape. Remi is useful for industrial application and for rough furnishing fabrics. Fibrous and non-fibrous impurities component of cellulosic fiber. Alpha cellulose is the actual fibrous material. Hemicellulose is the cell wall polysaccharide. It is soluble in 18% caustic soda solution. Pectic acid and pectin, these are insoluble in water but soluble in alkaline solution. Lignin is a complex aromatic polymers present in bast fiber, absent in cotton, soluble in sodium hypochlorite or sodium chloride solution. Fats and oils are solubilized by saponification, while wax having melting point of 60 to 80 degrees centigrade can be removed by emulsification in soap at high temperature. Nitrogenous compound, protein and polypeptides readily soluble in boiling alkali. Mineral matters, those are alkali earth compound, potassium and phosphate ions. Natural coloring matter, these are natural coloring matters can be effectively destroyed or made colorless by oxidizing bleaching agents. Chemical constituent of cellulosic fiber, percentage on the dry weight. Constituent alpha cellulose in matured cotton 88 to 96.5%, flax 70.3%, jute 69.7%, remi 79.1%. Hemicellulose absent in cotton, 18.6 in flax, 13.3 in jute, 14.6 in hemp. Pectin and pectic acid 0.4 to 1.2 in cotton, 2% in flax, 0.2 jute, 2.1 in remi. Lignin absent in cotton, 2.2 in flax, 13.1 in jute, 0.66 in hemp. Remi. Fats and waxes 0.4 to 1.2% in cotton, 2.6% in flax, 0.5% in jute and 0.3% in remi. Nitrogenous compound 1 to 1.9% in cotton, 2.8% in flax, 1.6% in jute, 2.1% in remi. Ash, that is inorganic salt, 0.7 to 1.6% in cotton, 1.5% in flax, 1.6% in jute, and 1.1% in remi. Other present in cotton is 1.7%. Animal fiber, silk. Animal fibers mostly composed of amino acid residues or protein. The most important animal fibers are silk and wool. Silk are secreted as filaments by the glands of larvae of different species of moth. Two broad types of silk are domestic or mulberry silk and wild silk, namely tusa or tosor, muga and eri. Wild silk mostly obtained from the bushes and trees in the wild. Silk possesses strength, elasticity, softness and sustainability for acid dyes. Mulberry silk is obtained from the moth larva Bombyx mori. Its share is about 80% of the worldwide silk market. Sericulture or cultivation of silkworm requires long and considerable experience and patience. 4 stages of silkworm are: number 1 egg, number 2 larva, 3rd pupa in the cocoon, and 4th adult moth. In rearing process, cocoons are soaked in hot water and then placed in water in a steam heated basin. 5 or 10 filaments are drawn together as a single thread. Wild silk. There are several wild silk varieties. Popular Indian wild silk varieties are: 1. Tosor or tusa, Anthrea millita. Number 2. Eri, that is Philosomia ricci, and 3rd Muga, that is Anthracia assamiensis silk. Cocoon of Tosor is about 4 times larger and much harder and browner than those of mulberry. Eri silk is similar to tusa or tussa seed but has a lighter natural color. It is harder and less lustrous than cultivated silk. It is difficult to reel the filament from their cocoons and waste spinning method is used. Muga silk is native to Assam state of India. It is either white or light brown in color. Silk filaments composed of fibrin embedded in silk gum, sericin. These about 20 to 30% weight by weight in mulberry silk and 5 to 15% wild silk. The sericin is responsible for harsher film removed by hot soap solution with or without little soda ash, that is known as digamine. The fibrin is much simpler in structure than wool keratin and composed of simple amino acids. Fibrin molecules align themselves parallel to each other and hydrogen bonds are formed, resulting in a highly crystalline and oriented pleated sheet structure. Silk fibers are smooth surfaced and triangular in cross section with rounded corner. Figure shows tussar silk, muga silk, and microscopic view. First one longitudinal, rod shape, and second one microscopic cross section of digam silk. It is having triangular cross section. Wool is a natural, highly crimped protein hair fiber of sheep. Worsted fabrics. These are highly twisted, finer wool yarn blended with polyester fiber. Woolen fabrics are less twisted yarn of coarser wool fibers. Wool composed of extremely complex, highly cross-linked keratin protein made of over 19 different amino acids. The most important amino acid is sulfur containing amino acid cysteine, which form cross-link through disulfide bonds between adjacent chains. Keratin differs from most of other proteins because it contains about 3 to 4% sulfur. Wool fiber, popular for warm clothes, becoming more costlier day by day and are gradually being substituted by synthetic acrylics. First figure shows how the wool is cut from the body of the ship, and second two are microscopic view of wool fiber. First one is a longitudinal view and second one is the cross-sectional view of wool fibers. Morphological structure of wool. Under a microscope, wool fiber appears as a solid rod with its surface covered with horny scales resembling fish scales. The scales project slightly from the stem of the fiber and point slightly outwards towards the tip. The coarser the wool, larger are the scales. The wool fiber is complex in structure and consists of three tissues arranged in successive layers from the surface inward. First, the epidermis or cuticle, then the cortex, and inside is the medulla. The figure shows cross-section and longitudinal views of wool fiber. The cuticle is thin scales of hard and horny consistency. These overlap and protrude for about 1/3 of their length, the end being directed toward the tip of the fiber. The outermost layer of the scales is a tough membrane called epicuticle. Beneath there is exocuticle and the inner layer is endocuticle. The cellular portion, about 90% just below the scale, is known as cortex. The central portion of the fiber is called medulla. Specialty hair fibers. Yes, specialty hair fiber, similar to wool in composition, are obtained from certain animals of the goat and camel families and are valued for valuable properties such as fine diameter, natural luster, and ability to impart pleasing hand. The goat family include mohair from the Angora goat and Kashmiri from the Kashmir goat. Fibers obtained from the animals of the camel family include camel hair, mainly from the Bactrian camel, and guanco, lima, and alpaca and vacula. Fibers all from the member of the genus Llama. In general, these natural protein fibers have better qualities but are costlier and are of limited supplies. The figure shows first one is Angora goat, second one is Kashmir goat, and then lima, alpaca, vacuna, and guanco. Man-made fibers. As against fibers obtained from natural resources, a large variety of fibers are made by human beings in the factories called man-made fiber in three ways. Number one, wet spinning, by passing dissolved polymer into a non-solvent, for example rayon and acrylic. Melt spinning, by passing polymer melts through spinneret followed by cooling, for example polyester, polyamide, nylon and polypropylene. And third type, dry spinning. Polymer solution is passed through spinneret when solvent is evaporated with hot air, for example acetate, acrylic, spandex. Man-made fibers are of three types: regenerated fiber. Natural fiber polymers are dissolved and subsequently regenerated as continuous strand of polymer called filament by passing through fine orifices called spinnerets. Synthetic fiber, those are made by chemical synthesis from simple chemicals. After polymerization, the melt or solution of the polymer is passed through spinneret and spun into filament. Refractory or ceramic and industrial fibers. For example, carbon fiber, glass fiber, metal fiber, etc. Rayon fiber. Rayon is a cheaper substitute for cotton, especially in blends with polyester. It is produced from eucalyptus trees and other sources like bamboo, cotton waste, etc. Viscose process uses alkali and carbon disulfide. Lyocell process uses eco-friendly organic solvent such as N-methyl morpholine N-oxide, that is NMMO, to substitute neurotoxic carbon disulfide which are used in normal viscose fiber, but the solvent NMMO is quite expensive. High weight modulus rayons or polynogic rayons are produced from high grade cellulose. Cellulose sodium xanthate prepared from alkali cellulose and carbon sulfide is dissolved in water and spun from a dilute sulfuric acid solution containing no additive. Polynogic fibers have very high tensile strength. The majority of viscose rayon has a serrated surface and irregular cross section, like due to skin, that is higher orientation. Filament is long and straight. The fiber is much less crystalline, only 30% than cotton, which is having 70% crystalline portion. High tenacity viscose rayons are more crystalline. Cellulose acetate fiber. It is the first man-made thermoplastic fiber. It softens rather than decomposes or ignites under sufficient heat. Hydroxyl group of cellulose are substituted with acetate group. Acetyl content ranges from 29% to 44.8%, corresponding to mono, di and triacetate. It is high heat resistance and less hygroscopic. All hydroxyl groups are first substituted to form cellulose triacetate, and then it is hydrolyzed by adding water. It is dissolved in acetone or methylene chloride and then dry spun with hot air. Under microscope, acetate fiber shows no longitudinal striations. The cross sections are irregular but in the shape of lobes and the indentation are not so deep as in case of viscose. Acetate is used in dresses, blouses, foundation garment lining, household furnishing, specialty fabrics. Triacetate is used for sportswear and for garments with high plate retention. Regenerated protein fiber. Prices of wool and silk are ever increasing since long vegetable fibers like groundnut, corn or peanut have been used for the production of textile fiber. Other protein fiber sources are also came into attention, like milk waste, casein and chicken feathers are also becoming potential source of animal fibers. Though these fibers are sustainable, but some of their properties like durability and strength are poor. As a result, their use till date is limited. In recent years, a number of sustainable protein fibers are developed from biomaterial. Most important is the casein fiber. A male casein fiber got certification for Okote Standard 100 in April 2004. It is very comfortable with excellent water transportation and air permeability. It is also healthier, light, soft and resistant to fungus, insects and aging. Its sulfur content is very low, only 0.17% as against that of wool. A soybean protein fiber was also first textile fiber from vegetable origin in 1937. The figure shows flow sheet of casein fiber production. Casein is mixed with caustic soda and water, then filtered, deaerated, spun into tow and then drawn, hardened, washed, dried, trimmed, cut and made into bale. Synthetic fibers produced from chemical substances mostly derived from petroleum products. Small molecules or monomers are joined together to form polymer by polymerization. Important synthetic fibers are nylon, polyester, acrylic and polyurethane. They are thermoplastic, that is softened when heated. At glass tension temperature Tg, the polymers lose rigidity. At a particular high temperature, the polymer melts. The dye uptake is also very low below its Tg. They are hydrophobic, do not absorb moisture, generate static charges on abrasion and durability is poor. They can be washed and dried quickly. Resistance to bacteria, mildew and insects like beetle and moths quite high. Lighter in weight, that is have low specific gravity, poor wearing comfort, absorb oils and greases, less flammable than natural fiber, melt and drip and form bed. Manufactured under controlled condition, much purer and whiter. Changing spinneret cross section, synthetic fiber may have round, tri-level, penta-level, dog bone, hollow or crescent cross sections. In bicomponent fiber, two polymers are arranged in a matrix side by side or sheath core configuration. Nylon or polyamide fibers, nylon 6,6, that is CH2,5CONHN, is prepared by step growth polymerization of hexamethylene-diamine and adipic acid, and it is melt spun at 280 to 290 degrees centigrade. Nylon 6, COCH24, CONH, CH26NH is prepared by ring opening growth polymerization of caprolactam. Both the fibers are melt spun and drawn mechanically to orient fibers following spinning. Degree of polymerization dP varies from 100 to 250 units. Both nylons are very similar in structure and properties. The amide groups make them reasonably hydrophilic and provide ionic sites for the dyes. Nylon 6,6 has lesser durability and little harsher feel than nylon 6. Nylon 6,6 melts at 262 degrees centigrade while nylon 6 melts at 215 degrees centigrade. Nylons are strong and stiff fibers with excellent resiliency and recovery from bending and stage for deformation. Their density is low and moisture again is 4 to 5%. They are soluble in phenol, formic acid and benzyl alcohol. Abrasion resistance is high and is used in rope manufacturing. Attacked by acids, bases, reducing agents and oxidizing agents under extreme conditions. At elevated temperature and under sunlight, nylon undergo oxidative degradation with yellowing and loss of strength. Aramid or aromatic nylon. Aramid or aromatic polyamide fiber are formed by polymerization of aromatic diacid dichloride with aromatic diamine in a polar aprotic solvent such as N,N-dimethyl formamide. The meta and para substituted benzene dicarboxylic acid chlorides are used for Nomex and Kevlar aramid fibers respectively. to react with diamine. Because of the linear parastructure, the molecular chains in Kevlar are extremely stiff and can be fully aligned in drawing operation. The aramids are the strongest man-made fibers. The fibers are stiff with excellent resiliency and recovery from bending deformation. Aramids have very high heat and electrical resistance. They have excellent insulating capacities and are unaffected by heat up to 250 degrees centigrade. They are extremely resistant to chemical and biological attack. The figure shows structure of Nomex and Kevlar fibers. Chemical structure of Nomex and Kevlar fiber. Nylon fiber are usually rod-like with small surface or tri-level in cross section. Polyester fiber. Polyester is the leading man-made fiber in production volume. It is most versatile alone or as a blended fiber. It is extensively used in woven and knitting apparel, home furnishing, industrial fabrics. Global polyester fiber production stood at 63.3 million metric tons in 2020. Polyesters are fibers containing at least 85% of a polymeric ester of substituted aromatic carboxylic acid. The major polyester in commerce is polyethylene terephthalate. The structure is shown in the figure, adjacent figure. Polyester molecules tend to pack tightly by drawing highly, resulting in van der Waals forces to play, causing a high crystalline fiber. The fibers are usually smooth and rod-like with round or tri-level cross section. Extremely strong fiber, relatively stiff and possess excellent resiliency and recovery from bending deformation. The fiber is quite hydrophobic. Polyester fibers are swelled or dissolved by phenols, chloroacetic acid or chlorinated hydrocarbon at elevated temperature. Heat conductivity is moderate and resistivity is high, leading to static charge buildup. Polyester softens at 210 to 250 degree and melts at 250 to 255 degrees centigrade. Highly resistant to acid base, oxidizing agent and reducing agent, and is attacked by hot concentrated acid and alkalis. Not affected by biological agent, polyester possesses poor durability and moderate flammability. Introduction of sulfonic group, acid group on the benzene ring of terephthalate leads to cationic diol polyester. Halogen, for example bromine, phosphonates groups make polyester flame resistant, especially if antimony oxide is present in fiber matrix. Surface modification of polyester with hot alkali is also done in certain commercial varieties in order to achieve silk-like softness. The figure shows microscopical, longitudinal and cross-sectional views. And lastly, polyester fabric. The acrylic fibers include acrylic, modacrylic and other vinyl fibers containing cyanide groups at side chains. The fiber containing more than 85 and less than 85% acrylonitrile are known as acrylic and modacrylic fiber respectively. The comonomers are methyl methacrylate, vinyl acetate or vinyl pyridine. The copolymers are either melt spun by passing through a precipitating solution or dry spun by passing through a hot air chamber. The figure shows acrylic fibers have two components. One is acrylonitrile and rest is vinyl based. Now if first one is expert and second one is Y part, if expert, that is acrylonitrile is greater than 85 and Y less than 15%, then it is acrylic. But in case of monocrylic, the first part, that is acrylonitrile portion, is less than 85 and vinyl portion greater than 15%. These fibers possess a warm, bulky handle, good resiliency and wrinkle recovery. The degree of polymation of DP is about 150 to 200. Acrylic fibers are fibers of moderate strength and elongation and break. The fiber is moderately stiff and possesses excellent resiliency and recovery from bending deformation. Moisture regain is low but higher than polyester. Acrylic fibers exhibit good chemical resistance to mineral acids and common solvents, only attacked by concentrated acids, and are slowly hydrolyzed by weak alkalis, unaffected by oxidizing and reducing agent except for sodium hypochlorite solution at elevated temperature. It is unaffected by biological agent and sunlight. Above 200 degrees centigrade, acrylic fibers softens and oxidized by complex mechanism. With the formation of colored groups in the fiber, it turns black. Acrylic fibers have a widespread spectrum of use where soft wool-like characteristics are desired, such as sweaters, skirts, dresses, suits, knitted wear, blankets, socks, carpets, upholstery, etc. Acrylic fiber usually possess smooth surface with long dog balloon create action. Polyurethane fiber. Polyurethane fiber or spandex is highly stretchable and elastic as rubber, stronger than rubber and resistant to aging. The fiber is dyeable freely and fine yarn can be produced. It is manufactured from glycol and diisocyanate as raw material by a special spinning method. Polyurethanes are very popular in sports clothing, used in the construction of running surfaces for the runners and jumpers, in the building mats for athletes, and in combat sports, in the construction of ships and their protection against water petrochemical compounds. Like specific gravity of cotton is 1.5 to 1.8, flax 1.8, jute 1.48 to 1.5, wool 1.28, silk 1.25 to 1.30, viscose 1.46, polyester 1.34, polyamide 1.14, monocrylic 1.16. Fiber diameter millimeter: cotton 0.014 to 0.016, jute 0.02, wool 0.17 to 0.4, silk 0.009, viscose varies, polyester varies, polyamide varies, monocrylic varies as per spinneret and as per end requirement. Moisture again: cotton 7 to 8%, flax 10 to 12%, jute 10%, wool 14 to 16%, silk 10 to 11%, viscose 11 to 13%, polyester 0.4, polyamide 2.48 to 5, monocrylic 1.2 to 2.5. Initial modulus: cotton 4, flax nil, wool 2, silk 7, viscose 5, polyester 6, polyamide 2, monocrylic 6. This is gram per fiber per tex, gram force per tex. Now tenacity: cotton tenacity is 19 to 46 gram per tex, gram force per tex. Cotton 19 to 46, flax 19 to 54, jute 31 to 0.5, 31.5 to 40.5, wool 11 to 14, silk 39, viscose 20 to 51, polyester 25 to 54, polyamide 32 to 65, modacrylic 18 to 30. Elongation at break: cotton 5.6 to 7.1, flax 3, jute 1 to 1.12, wool 29 to 43, silk 23 to 24, viscose 8 to 20, polyester 12 to 55, polyamide 16 to 65, modacrylic 20 to 25. These estimates are approximate and valid in general. Significant differences may be observed, especially for synthetic fiber, depending on the manufacturing conditions. Microscopic identification of textile fibers. Cotton: convolutions in longitudinal view and variable shapes and size of cross section with large hollow channel called lumen. Jute: nodes and variable lumen diameter in longitudinal view. Cross section shows bundles of fiber. Outline of the cross section polygonal and lumen circular or elliptical. Viscose layer: numeral striations under longitudinal view and serrated outline of the filament under cross sectional view. Acetate trail: bright filaments, heavy striations in longitudinal view, irregularly lobed cross sections. Polyester: longitudinal, featureless rod-like cross section, circular or other shape, depends on spinner's shape and spinning condition. Nylon: featureless normal nylon shows specks or delastering agent. Trilobar or profile nylon, longitudinal view shows broad shadow line due to indentation between the lobes. Acrylic Orlon 542, ribbon type twist with peanut-like or elongated cross section. The test: the chemical structure of the fiber determines its solubility in various solvents and provide a simple but accurate identification of the fiber. Cotton: solvent is cuprylamine hydroxide solution, 70% sulfuric acid. Flax and jute: dissolved with brown color in 70% sulfuric acid. Wool: dissolves in 5% caustic soda at boil. Vapor blackens lead acetate paper. Silk: dissolves in 5% caustic soda solution at cold. Viscose: dissolves in cuprylamine hydroxide solution and 60% sulfuric acid. Acetate: dissolves in acetone. Polyester: dissolves in hot M-cresol and hot M-chlorophenol. Polyamide: dissolves in hot M-cresol and 50% formic or hydrochloric acid solution. 90% formic acid or hydrochloric solution. 60% sulfuric acid solution. Acrylic: boiling dimethyl formamide. Test of textile fibers. The reaction of the fiber to open flame is a useful guide in the identification of fiber. Natural fibers and regenerated fibers will burn to ashes with a characteristic smell. Thermoplastic synthetic fiber will melt, fuse and sink, forming heartbeats. Cotton and regenerated cellulosic fiber like viscose will burn quickly with the smell of burning paper, leaving little or no ash. Protein fiber, for example wool and silk, burn slowly with the smell of burning hair, leaving easily crushable black beads. Acetate fiber burn and smell with smell of vinegar or acetic acid, leaving hard black beads. Polyamide fiber form glossy beads with the smell of amines. Polyester fiber produce irregular beads with an aromatic smell. Polyacrylic fiber leaves small hard black beads. Other fiber identification tests. Specific gravity test. A series of solvent mixture of varying density may be prepared. If the specific gravity of fiber is greater than that of a particular solvent mixture, it will sink, and if less, it will float. Staining test. Fibers have varying dyeing affinity for different classes of dyes. Dye mixtures of different classes may be used to check the fiber type. Two or more staining agents may be used to confirm the fiber content. Other analytical tests: optical and electron microscopy, X-ray diffraction, infrared spectroscopy, ultraviolet visible spectroscopy, thermal analysis, elemental and end group analysis, etc. I hope you will find the video informative. Please comment. Please share the video to your friends and others. Don't forget to subscribe. Please don't forget to subscribe. Thank you.